Good afternoon, everyone. My name is Hani Nassif. I'm a professor at Rutgers University. And today it's my pleasure to introduce the speakers for this interesting webinar. This webinar is about what RIME and C2Smart have been accomplishing over the last probably 10, 15 years in crashworthiness. And in particular, I'd like to introduce our main speaker today, who's Dr. Wassim Nasreddine. Wassim has been very active in our group, and he has been leading this effort in the simulation and the crash analysis for bridge barriers and road safety hardware. And Wasim has his PhD from Rutgers University, and his undergraduate and master's degree are from the American University of Beirut. And he's been with us as a research associate for the last 3 years after his PhD. And not to my surprise, he has been doing extremely well in this area. And also in attendance today, Dr. Ali Atahan from CalSpan, our partners in the testing. CalSpan, for those of you who are not aware, is a testing facility in our neighborhood here in Buffalo, New York. We've been working with them for multiple years, and they've been active and successfully completing a large number of tests for our sponsor, the New York State DOT, which by the way, would like to acknowledge them for their support and for guidance and technical support for the group. Also, I'd like to thank C2Smart, the center with our colleagues, Director Dr. Kaan Ozbay and Dr. Frank DarConte, who has been managing this project for New York State DOT. Without them, this project would not have been really taking place. C2Smart has been an intellectual one-stop shop for us in many aspects and dealing with interesting projects. So I'd like those of you to really visit the website C2Smart and learn about the different projects, including this particular one. We just completed I would say maybe 9 different barriers, Ali, for the CalSpan successfully. These are, speaks about their ability to really turn it around quickly. And we visited their facility a couple of times. It is very accessible, and I encourage all the attendees from other DOTs in the area to please reach out to us and to them to help you in your project. So without any further ado, I'd like to also, without any, there are other speakers, but also Chaekuk Na, Dr. Chaekuk Na has been involved in the effort. So I'd like to invite Wassim to go ahead and get started. Thank you.
Yeah, thank you very much, Dr. Nassif, for the introduction. It's my pleasure to be the speaker on this interesting topic. I'm sharing now my screen. Please let me know if you can see it properly.
Can you? Yeah, now it's in the presentation mode. Thank you.
Okay. All right. So today's presentation will be about the crashworthiness analysis, simulation, and model validation of roadway and bridge hardware. This work has been done by Rutgers Infrastructure Monitoring and Evaluation RIME Group in partnership with New York University, with CalSpan, RoadSafe LLC, and New York State DOT and New Jersey DOT. So the presentation will cover first the standard. Why do we certify? Why do we certify the hardware, and what hardware do we certify, and what are how MASH replaced NCHRP 350. Second, we will cover the test levels and the fleet of vehicles. We have several test levels, compliance vehicles, and occupant risk criteria. Then we'll talk about the workflow. So first, the design, then the finite element simulation, the assessment, and finally, the crash test, validation, and certification if needed. We're going to go inside the model, which we use the LS-DYNA software for, modeling of vehicle barriers, connections, soil, and vehicles. Then the verification and validation procedure. How do we look closely at the model and how we tell if what we are seeing makes full sense or not, based, of course, on the real test results. And we will go over 3 case studies that we did for this project with New York State DOT, and finally share the lessons learned from this project. Okay, so first we're going to talk about barriers, because mainly when we talk about hardware, the safety hardware that we are trying to assess, that includes mainly the barriers. Now, of course, the barriers, there are many types of barriers. We have guardrails or guide rails, as we call it. We have medium barriers, bridge parapets, and transitions. And barriers can be either concrete or steel. They can be cable barriers. There are several types of barriers. And the main role of the barrier, as everybody knows, is to contain and safely direct an errant vehicle, of course, without excessive occupant risk, a structural breach, or debris hazard. Full-scale crash tests are the benchmark, but of course they are expensive, and it's very hard to replicate them or to do them over and over. So, and a crash almost always lasts less than 1 second, but we have to understand what happens in each and every millisecond, because the damage that occurs, the snagging that might happen, the risk, the occupant risk that happens to the passengers, they all happen within those milliseconds. Okay, so this is about the barriers that we mainly assessed in this project. We have several types. The guardrail or the guide rail that you see it usually on the roadside, and it's only from one side. The median barrier is what separates traffic from both sides, and it's symmetric. So whether it's impacted from departure or approach side, it would behave the same. We have the bridge parapet, and these are usually more rigid because we don't have margin for deformation as in a roadside barrier. And we have the transition. The transition is the junction between two barriers, usually the bridge barrier and the roadside barrier, and it, as its name, transition, so it makes a transition in the stiffness or rigidity from a less rigid barrier, which is the guide rail, and a more rigid barrier, which is the bridge rail. Okay, so the standards for assessing the roadside barriers. Previously, it was NCHRP reports, report 350. That was the first standard published. And before that, every test facility have their own criteria. Since 1993, NCHRP was the benchmark for assessing the safety of roadside barriers. Then it was replaced by MASH in 2009, where the first edition was published by AASHTO, and another edition replaced it in 2016. And now any installations, and even all installations, are being reassessed according to MASH criteria. Now, what does MASH criteria look at? Looks at several things, but mainly the structural adequacy of the barrier, or any roadside hardware, but mainly we're talking here about barriers. So barriers are supposed to contain the vehicle and redirect it. Um, and the main connections have to stay intact, anchors or splices or whatever. Um, and of course, they look at the occupant risk, so the safety of the vehicle passengers, mainly occupant impact velocity. We'll define these later, and write down accelerations. They have to stay within limits, and also the vehicle trajectory. The vehicle shall not roll over, shall not go through the barrier, and no hazardous re-entry into the traffic. Okay, so there are several test levels for barriers. So as we know, barriers are not equal. There are some barriers which you see on the highway, some others on local roads, and each barrier has been assessed at a certain level. So we have test level 1 through 6. At level 1, we have the low speed barriers, and these are the smaller barriers, and they are supposed to redirect traffic at 31 miles per hour. Test level 2, these are barriers used on local roads, and they are tested at 44 mile per hour vehicles. Then test level 3, that's the most common. That's for highways, where the barrier is assessed based on an impact at 62 miles per hour with a car and a pickup truck. Test level 4 as to test level 3, 10-ton or 22,000 pound single unit truck at 56 mile per hour. And then we have test levels 5 and 6, which add a tractor trailer and a tanker trailer. Now, Now the small passenger car, otherwise referred to as 1100C, that's its weight in kilograms, so 1100 kilograms. This is its weight in pounds. And the impact is done at is optimized to be at a 25 degree angle. So for the pickup truck, which weighs around 5,000 pounds, also at 25 degree with the same speed. Now the 10-ton single unit truck is impacted at a lower speed, 56 mile per hour, and a lower angle, 15, and so for the tractor trailer or the tanker at 50 miles per hour, 50. Now the occupant risk limits, the occupant impact velocity and occupant risk assessment, they have limits set by MASH, preferred limits and hard limits. And we're gonna talk about them here. Okay, so the occupant impact velocity is the velocity of the driver post impact. So we want that to be limited because a higher velocity would very much increase the chances of a very hard impact between the passenger and the inside of the vehicle. That was so this is specific for the car and the pickup truck because it assumed a free travel within a space of 24 inches by 12 inches. So the occupant impact velocity is something that we look at in both the pickup truck and the passenger car, and it's not used for the bigger trucks because of the bigger space. Its hard limit is 40 foot per second. Anything beyond that is considered a failure, and a modification or adjustment has to be done to the test article. The preferred limit is less than 30 foot per second, and it's evaluated in both directions, which means X and Y, horizontal through along the test article and perpendicular to the test article. As for the ORA, it's occupant. We call it occupant risk assessment, and it stands for also for occupant write down accelerations because that's what it is. It is the highest 10 millisecond average deceleration that follows the impact. We want to so that's measured in G's, and the limit that is set by MASH is 20.49 Gs. The preferred limit is less than 15 Gs. Of course, we know Gs is what there is a certain limit that a human body can sustain without injuries. So 15 would be the preferred limit, but anything beyond 20.49 is considered a failure. Another component that we look at is the occupant compartment deformation. So aside from the velocity and the acceleration during and after impact, we look at the deformation of the of some components of the car. Mainly, we have the floor pan, we have the door, we have the top part of the toe pan, the roof, the windshield, everything. But almost always the governing compartment would be the floor pan and the door because of their close proximity to the wheel. So usually when the vehicle impacts the barrier, we have a lot of deformation of the wheel, and sometimes there is an intrusion towards the. You can see this is a video. So you can see how the wheel goes through the floor pan and results in a very high. In this case, it was like 8.5, which is slightly close to the limits. So why is this dangerous? Because any excessive deformation would result in injuring the passenger or even the driver, depending on the side of the impact. And there are limits set based on the compartment. So the floor pan's limit is 12 inches. The door limit is 9 inches. And if the occupant deformation exceeds that, that would be considered as a failure. And it's worth noting that usually the small car reaches the OCD limit before the pickup truck because of the limited space that's between the wheel and the floor pan or the door. So that what governs sometimes the test. Okay, I have to. All right. Okay, so how a barrier earns MASH certification? Okay, so this is the list of steps before we reach the validation. So first we have the design and geometry. We have the DOT drawings. We have to capture each and every detail, and the details are a lot. So we go down even the washers, the bolts, the nuts, every small components would be modeled very accurately. And after we get all the different the dimensions and the properties of all the different parts, we build the finite element model. We use LS pre-post, which is open source to whoever wants to look at it. You can build any geometry you want. We do for each and every component of the test article, including barrier, post, soil connections, and the vehicle. And we're going to talk about the vehicle because the vehicle is already built by some other test facilities. And then we simulate the impact. So using LS Dyna, we simulate the impact. The vehicle goes through the impacts the barrier, and we do it at several points. Of course, because once we use finite element modeling, almost the most important thing is to identify the critical impact point that has to be tested. So our role in finite element models, and when we do the finite element modeling, is to first make a full assessment. But to be able to make a full assessment, we have to impact so many points, and we do it every foot or half foot or 2 feet of increment. So we keep moving the vehicle to different locations and do the impact. And depending on the test level, we select the degree, the angle in degrees, 25 or 15, and the speed 62 or 56 or whatever. And then we assess after the simulation ends, we assess all these parameters against MASH requirements, and we sometimes have to modify the finite element model if there is any, not even the model. Sometimes we have to modify the whole article. So if we find a critical failure, we would propose a certain modification before the crash test is done. And then after everything is prepared, we go and do the full scale test. And then we go back to our model and see how it compares to the full scale test. Okay, so as I mentioned, we use AASHTO to do the simulation, and AASHTO does the equations of motion with explicit central difference time integration, which is the right tool for a short content-rich event. We have large deformations, we have buckling and fracture, and we have thousands of interactions. All the parts interact together, and they mostly do undergo nonlinear deformations and reach their nonlinear zone. And we do that, let's say, for a full test lasts for 1 second, the whole impact. Because we're doing explicit time integration, we have to do it at very small time steps, because otherwise we would risk the instability of the model, and then it stops. For our case, 5 microseconds of time step, so we will be looking at the whole model every 5 microseconds. So for a full test, we have 200 steps, and at every step, the software undergoes a whole lot of mathematical computations, because we have, as mentioned, millions of elements. They're mostly nonlinear and contact driven. And to be able to run these huge models, we use our cluster at Rutgers, which is a series of very high-end computers. We do the distributed memory one, where we can run up to 280 CPUs for every case, and that if we go up to 280, we can finish the model in 1 day. Otherwise, if you use less than that, it can go up to 4 days just for one case. And remember how many cases we have, how many impact points, how many test vehicles we have to use. So it requires a lot of time. So as for the modeling, every structural component is modeled and meshed appropriately, so if we do use a very small mesh, we increase the runtime, and if we use a larger mesh, then we have to reduce the time step, so that doesn't help us. So all of that is optimized. Of course, concrete elements are modeled as solid elements, so are bolts as beam elements, but the heads and the nuts and all of that are also solid elements. Soil elements are solid elements. Rails and posts are steel rails are modeled as shell elements with 5 integration points to capture the deformation. And all of these elements were calibrated, were tested by different facilities. So this is what we receive, a drawing, and this is what we transform it to. In this case, you are looking at a barrier anchored to the deck as such. In fact, this barrier was tested last week by CAD-SPAN. So we have the barriers connected. You can see the mesh here for the concrete barrier, and we have a steel anchor going through the deck, and we have the deck reinforcement and the barrier reinforcement here, and a connection plate. So there are a lot of details to pay attention to. And this is another article that was also tested a month before that included a concrete parapet with a fence, and the fence required a lot of elements to capture. Now that's something that we spent a lot of time to optimize because we had almost a million elements of beam elements for the fence, and you can tell how many contact interactions are there. So that also required we had to reduce also the time step because we got some non-physical added mass, and that resulted in termination of the model. So sometimes we have to fine tune it to work the best. Okay, so we talked about the hardware that we mainly do, but we didn't talk about the vehicles. Of course, the vehicle is much more complicated to model because there are many components like the suspension, the wheels, the pressure, so there are a lot of details. So that is something that is done by other test labs. Mainly George Mason University in Virginia does that, where they acquire a vehicle and they tear it down. They scan each and every part. They digitize the geometry. They test the components. They mesh the elements, characterize the materials, and then validate it. So they validate it by crash testing the whole vehicle, and then the finite element model is published. Now these projects are usually federally funded, so that's why you can merely go to George Mason University website and download the vehicles. So vehicles have almost a million elements depending on the vehicle. Larger vehicles have less elements because they are bigger, and you can find the finite the model for in LS Prepost for the car, the pickup truck, and the single unit truck, in addition to the bigger vehicles as well. So these are the different vehicles that you can get from there. Now they try to not increase the number of elements, which actually they might need to increase it more, but they try to make it this much only, just for to reduce the time of running the model. So if you like Tesla, for example, they have north of several million elements, but they have more computational power than available to the public. So they try to keep it less than 1 million. Okay, so as mentioned before, the way we do it is we have to assess the structural adequacy, the occupant risk, including the OIV, ORA, and occupant compartment. We have to check for any snagging or pocketing, and that mainly happens when the rim or the door is captured by any gaps that are inside the barrier. So and that could increase the deceleration if the car was caught in any gap. And we have to look for any energy and debris. That's mainly a determinant of failure over bridges. So if we have a certain barrier and if we have components falling from the top, that would be a failure despite having everything else within the limits. Okay, so this is a verification and validation of the soil model. We use Drucker-Prager for the soil and LS pre-post for those who are familiar. Of course, solid elements. That was so, but we have to change the parameters so as they comply with the soil at the testing facility or the test site. That's an example of something that was done by Midwest Testing Facility. And we have good correlation between the FEA and the test, as you can see. And this is another validation for the fence, and that required a lot of effort because the fence, when the fence is built, there's a little bit of slack between the knuckles, so we had to remove slightly optimize that gap so that we can have a good agreement between this is the model and this is the test. This was done by TTI. This model was done by our partner Chuck Plaxico at Roadway LLC, and you can see this is the comparison between the test and the model. Okay, so now I'm going to talk a little bit about 3 case studies, what we went through and what was critical. We tested actually we tested at Calspan in Buffalo, New York, a median barrier. Of course, before the test, we had the simulation done, and the simulation did show that the article passed. Okay, so we checked all the parameters, all the limits set by MASH, and everything was okay. However, when the test was done, we had a complete failure, and there was a reason for that. And I'm going to show you the video. Okay. Of course. Sorry. Yeah. Okay, so sorry about that. For some reason, the video is not. Let me try to open another one. Just one second.
Wassim, I believe when I tried to change the format, I might kind of didn't copy the video itself. I just copy it as an image. Might be the problem.
Yeah, that might be the case. So we're sorry about that. I just need 30 seconds to get the videos because they're interesting to show. Okay.
I think you may need to change the share the other screen maybe.
No, I'm just gonna.
Oh, copy paste in here.
Yeah, I'm just gonna copy the video here. Where are we? Okay, so this is the one, and this is the one, and this is the one. Yeah. All right. So I'll share again. Let me share again. Okay.
No, you're sharing your screen. Yeah, that was good.
Okay. So above you can see the crash test, and down you can see the simulation. So the main distinction was that the median barrier fell off, and that's considered a failure. It's not supposed to do that. But in the simulation, it was okay. It did not fail completely, just some expected deformation. So that was the previous simulation. that we had. And this was the crash test, and that was a failure. So we looked into why did that happen, and we could identify two things. First, the bolts that are holding here failed prematurely, and you can see that these posts stood straight. Surprisingly, they stood straight. So the weak point was definitely the bolt. Now, when we looked at the mill certifications, the material properties of the components of the test, we found that there was a big difference between what we used and what was supplied by the contractor. And surprisingly, what we got was very strong posts and weaker bolts. So since we have strong posts, all the forces were transmitted to the weaker bolts, and the bolts sheared off very easily, and we had that failure. So we had to change this in our model, and here's what we got. Okay. Simulation. Okay, that's also all right. So now we have the modified simulation, and you can see. So this is the same test, and this is the modified simulation. And you can see that we were able to get that failure by merely modifying the bolt properties and the post properties. So you can see different, let me play it again.
Wassim, I think you are not sharing the correct screen. You are, I see the same video that you showed earlier.
So the one that I showed earlier was the one that did not fail here, but this one failed here. Do you see the distinction? So this was what I showed previously. We had the barrier hold tight. So the top three are the same, but the bottom three are not the same. You can see that we had a full failure here of the barrier. Do you see that?
Oh yeah. Okay. Sorry for that.
Yeah. So that's only by modifying the properties of the bolts and the posts, we were able to find. Okay. Yeah. All right. So. Okay, let me go a little bit faster because we spent some time just to get the videos. So we proposed a certain modification which was only increasing the bolt size. That was an easy modification. We also ran the same test, and we had it work for both the finite element and the actual test. Now another case study that we had a box beam median barrier, and we had to do the TL3 criteria, and for TL3 criteria we're supposed to do both the car and the pickup. Okay, and what we did, we had we ran the pickup truck, and everyone assumed, okay, so if you have to do TL3, just do the truck and let's see what happens. The truck passed everything. The article was all right for the truck. Everything was below the limits. However, we said that let's do the car, and surprisingly, the car covered several times. So the first time, the car failed in occupant compartment. You can see that how much the compartment moved here. So it exceeded the limits. Then we did a certain modification. We added a rail, and then there was plowing into the soil, and that resulted in a complete overturning in the car. And that happened from both sides. So we had to do several modifications and that's all before the crash test. So we were able to propose several modifications before the test. And it's worth noting that these are trial articles. None of them are yet implemented, and that's why New York State is doing all of this assessment before implementing them. And another one was selecting the CIP for the barrier with a fence, and we had to run several cases. And mainly, we were looking at any compartments falling, because usually when we have a fence, then that means that the bridge that would be for a bridge over traffic, and we don't want any poles, any rails falling from the top due to the impact. And we had also to run several tests on this, and we were able to reduce and sometimes and Ali can talk more about that if needed. We have to make some judgment, because in the finite element we could model a bigger article, but when it comes to the crash test, it's not all needed. So we could modify or shrink it just to make it less costly, because there are some components that do not contribute to the behavior of the article. Okay. All right. So I'd like to share the lessons that we learn. Often connections do govern, despite being small. Bolts, splices, anchors, especially if there are any gaps between the splice and the rail. Sometimes they govern due to snagging, due to failure. So these should not be overlooked. And second, it's not always that the bigger vehicle is what governs, although when we talk about TL3, we have to test a car and a truck. To talk about TL4, it's car, truck, and single unit truck, all three together, and that simulation and testing, and sometimes it's the smaller car which governs. And the importance of finite element is it allows us to run so many cases, so many simulations before making any decisions. So as built does not mean as designed, which means that sometimes we have to change the design, make several modifications, of course, with the approval of the sponsoring agency. And as mentioned before, in finite element, we hunt the critical impact point, the one that's most likely to fail. And if that does not fail, then we have a higher likelihood that we will pass the crash test. And it's mostly about knowledge and saving. It tells us, so we are validating our design that's done using design standards before for the complete validation and perhaps certification through the crash test. Okay, so I'm concluding now. We want to de-risk the test, we want to cut cost and time, and we want to ultimately have safer roads. I'd like to acknowledge C2 Smart, New York State DOT, CalSpan, and RoadSafe for their partnership on this project. And I'd like to thank you for your attendance. I'm happy to take any questions you might have.
Okay, thank you, Wassim. I think let's look in the chat if there are any questions.
Yeah, I think there is one question on the Q&A from Samar Rabi from NCHRP. He's asking, what was required to get the NCHRP balustrade plus discovery bridge parapet eligible for Tier 4 by Federal Highway? What modification would be needed for Tier 5 consideration? Is it just the height, or are there other factors? Maybe Ali, maybe you can answer something, the testing requirement difference between Tier 4 and Tier 5.
No, this is specifically about the project we did, Chaekuk, for the balustrade. for the Pulaski. So let me comment on that. I think at the time, this was an open post and beam, open balustrade. It was the historic one that was implemented on Pulaski Skyway Bridge. And at the time, we redesigned it and to make it really MASH compliant. And the design was reviewed by ACOM, and then we modeled it. We tested it with the model, and then we went to TTI and we tested it at TL4. However, there was a little bit of discussion at that point. By the way, it passed, and for TL4, and the design was really performed extremely well. So we were thinking about, as the question that maybe this could be TL5, given that it's kind of a historic. I know a lot of counties have asked me personally and DOT to use it, and it's been implemented in California and other states, and including counties in New Jersey, where they implemented this historic type of balustrade. To implement it to TL5, I believe that it might need to be a little bit higher than what it is right now. I think it is, if I remember correctly, it is at 42 inches. It might need to be at 44 just to make sure that the larger vehicles, most of their chassis are now 48 inches above ground, and that could be a factor that we need to make it higher so it doesn't roll over or doesn't slide over the one. The other one is, I think the design needs, maybe the opening needs to be adjusted so that it is a little bit more rugged design. That could be done by doing a little bit more simulation. We can modify the design to make it take the 5-axle trailer rather than the box truck. So I think that there might be some work. I think we still have the models from the past. If there's interest to really improve it and make it more TL5, I think we can redesign it and make it more compliant. I don't know if that answers the question, but Ali, you wanna, in general, talk about the difference between TL4 and TL5 from your perspective?
Of course. Yeah. Thank you. Yeah, thank you for the explanation. Well, MASH test level 4 requires 3 tests. A car, 1100C, Wassim mentioned, 2270P pickup truck, and in addition to that, a box truck test. That is called 412. So those 3 tests, when the test article passes successfully MASH criteria, it is TL4 compliant. When it goes to TL5, it becomes the third heavy vehicle changes to 36,000 V. So it is a much larger tractor trailer, 36,000 kg tons, kilograms, of course, and that would require, of course, a much bigger kinetic energy impact on the test article. So assuming that the system is strong enough on the bridge or on the roadside or in the median, that test requires a much stronger and stiffer system to pass for a TL5. So the difference between TL5 and TL6 in summary is the kinetic energy of the heavy truck. Other than that, 1100C and 2270P tests remain the same. And the third test would be a much higher demanding test. That's the difference between them.
Thank you, Ali.
Of course. Thank you.
Any other questions?
Yeah, I don't see any additional question in the Q&A. Okay, another question have Samar Rabi again from DOT. Since EV are heavier than standard cars, will that change design standards, testing requirement, and weight in the future?
Yeah, I think I can. Wassim, you want to take that? I think I just want to say that there is currently a little bit of thought on trying to perform more testing and more modeling I think Calspan has done at least one testing, my understanding, and I think New York State DOT is interested in pursuing more work on this area. And definitely the electric vehicle, I mean, there, as Samer mentioned, he's rightly, so that they are heavier, plus their design is slightly different. So the road safety hardware, especially with the beam and the post, they might need to be re-examined in light of that. Ali, you want to talk a little bit about what you have done?
Sure.
I think you did a couple of testing on that.
Sure. So as Wassim and Dr. Nassif mentioned, MASH testing is, let's say, a TL3 system requires two tests, 1100 and 2270p test. Those are all the current roadside safety designs are tested with standard vehicles, which is 1100 kilo and 2270 kilo pickups. Now, once the electric vehicles become prevalent and they are now spreading in the country, those type of impacts are much higher, 30%, 40%, 50%, depending upon the weight of the electric vehicle and the car and the pickup. It's more impact energy on the existing hardware. And recent crash tests on the W-beam and tri-beam systems show that those systems need some kind of strengthening. So the test failed, and now the community, as in general roadside safety hardware community, is working on retrofitting or getting new designs. Nice DOT has an alternative because they're using cable barriers and box beam barriers more frequently on New York highways. And recent test on a cable barrier, nice DOT cable barrier, already successfully passed a Tesla Model Y MASH 3 level testing. I'm saying MASH test level 3 because of the speed and the impact angle are MASH. However, the vehicle weight is higher. So currently we have a cable barrier, passed the test with an electric vehicle, and more companies are working on MASH compliant systems with electric vehicles. And as Dr. Nassif mentioned, that NICE DOT is considering running box beam crash testing using electric vehicles. Yes, there is a demand, and DOTs are working on their designs to get the MASH compliancy on those designs with electric vehicles.
Thank you, Ali.
Thank you.
Wassim, you want to add anything to this? I think we were trying to.
Yeah, I think you and Ali have covered it excellent. So I don't have anything to add.
Thank you. Okay, I think we're coming close to the time. You want to play the video again? I know that you had hard time with some of the videos. I don't know if you want to share, if just to while we have like.
Yeah. Okay. Yeah. That was a glitch on our side. So
When I checked it, it was working. I don't know what happened.
yeah. So
until
for
you
some
get
reason,
the videos right, let me comment. With the help of Rutgers and the team, it makes our life easier as Calspan because we have the worst case scenarios every time identified. So we save a lot of time, effort, and cost on these tests since everything is prepared for us, and we run a test with the data provided by the team, Rutgers team, and thank you for that.
Yeah.
Yeah. So which video are you showing?
Yeah, that's the modified simulation after the.
It's kind of small. Can you enlarge it, make it a little bit bigger, maybe?
Yeah, because there are 6 videos, so they had to be smaller videos. So this only shows like how the small modification and material properties would change entirely the result from pass to fail. It's just the bolts, and so 20% perhaps increase in the and that's counterintuitive actually. To have the posts, stronger posts would lead to failure of the whole article. Like you wouldn't mind if you request 50 KSI posts and getting 70 KSI posts, right? But that led to the failure of the system. Why? Because now this is a strong point. We have a weak point, which is the bolts. So if we have stronger posts, then we require stronger bolts just to balance. So that was a great lesson that we learned.
Oh, thank you, Wassim. I think we're coming to the end here. So I want to again thank all the attendees for their time. I think this is we've been working on this interesting developments in these projects. We are so fortunate to have New York State DOT support our work, and also more fortunate to have CalSpan in our area as a partner, as a very reliable partner, where they have made an investment to really start the highway testing. And as you can see, this is their facility where we performed. I don't know, Ali, is it 11 tests so far? Maybe more. I lost count.
I think 12,
Last, yeah, over the last 3 years, this has been accomplished. So I'm really appreciative of the setup. Smart has been our one-stop shop for this, and I want to thank them for their help and support, especially Frank DarConte, who's been the maestro in this project, managing all the logistics and all the work that has been done. Without him, we would not have been really able to finish this project. And in particular, I want to thank Eric Lancy and Terry Hale for their enormous support and technical experience in this. Without them, we would not have been able to really get going. So again, I want to thank everyone involved, including my team on this. This has been great. Chaekuk, you want to maybe you and Mike announce the next one coming?
Yes, this one.
Yeah,
Yeah,
I can take
Mike.
that if you don't mind. So everyone, thank you for coming to this presentation. The next one is scheduled for August 27th at noon. So we'll be happy to see you there. The topic is going to be on GFRP rebar and non-metallic reinforcement in general for bridge decks, specifically for use in New Jersey. So that includes CFRP post-tension cables and other materials that are in widespread use now. We're going to do specifically for New Jersey. We're going to look at coastal and high salt usage bridge decks and some LCCA, so life cycle cost analysis, to go with that from existing literature and research. So we'll be happy to see you there, and it does look like it is time. Professor, if you want to say anything.
Yeah, I just want to mention that this is an active project sponsored by the New Jersey DOT for the Bridge Resource Program. And we are investigating the use of GFRP rebars and bridge decks, as well as other non-metallic. So I want to thank them for their support and leadership. I'm not sure who is in attendance today, but I want to thank them for their Bridge Resource Program. It's allowing us to do this series of webinars and bring in all the speakers. So I want to thank them specifically for their support. With that, I want to thank everybody for attending. Out of respect of the time, I think it's 1 o'clock. So thank you again, and please come to this Bridge Resource Program webinars. The use of GFRP rebars. I visited their plant in North Carolina. It's really becoming very prolific in the US, the use of that. So please attend this webinar, I think, or share it with your colleagues, because this is going to be a game-changing, in bridge decks and future, infrastructure. Thank you, everybody.
And just quickly, the registration link to the Zoom is in the chat.
Oh, okay, great. Thank you. So we'll give them a couple of minutes to get the chat link. And Liz, thank you for help in this seminar. I know Smart has been really great in doing the technology transfer for us. So I want to appreciate your help and thank you for that. Okay, with this,
Thank you.
thank you everyone, and look forward to see you on August 27th. Have a wonderful day. Bye-bye.